All right, graphing trigonomic functions. This is Unit 4. This is by me, and this is the unit packet for extra credit for Mr. Mori's class. So starting off with the unit table of contents. Now, the majority of this slideshow is about 40 slides, and so I'll be going over all of these 4 points about simultaneously, and it has a bunch of graphs of various functions, and then we also move on to these 4, which is also bunched up into one huge section. So first off is the graphs of trigonomic functions. Now, in order to fully understand what a trigonomic function is, we must fully understand what a unit circle is. Now, a unit circle is what you see here, and these are the coordinates of each of the points. For example, this point here has a coordinate of root 3 over 2, root 3 over 2 being 0.866, and so you look at this is the x-axis. Notice how the radius is exactly 1 unit long, and so 0.866 lies around here, which is about right, and 1/2 is about half because the y-axis here is approximately a half over here. And then you would also have the unit circles of 30 degrees, 45 degrees, 60 degrees, and it goes all around the circle. And if you were to lay this out into one flat line, then it would give you the sine graph like this. So then these are the heights, and this is what the unit circle is used to derive the sine graph of. And then the cosine graph is similar to the sine graph, but it also starts at 1 rather than starting at 0. Now, the tangent graph is another trigonomic function that's slightly different from the cosine and sine graph in that it has asymptotes. And now asymptotes are these dashed lines here that pretty much restricts the yellow line from touching it. So then you can see that there are multiple yellow lines here, and that each of these yellow lines are restricted and they can't touch this. Now, this line can't touch it and this line can't touch it. So pretty much any number in between here exists on the y-coordinate except this point here, in which no number exists on the y-coordinate, and that they also have different periods. For example, rather than having 2 pi as a period like cosine and sine does, it's got 1 pi. And moving on to the next section of amplitude, period, and phase shift for a trigonomic function with examples and pictures. Just to remind you of what a parent function looks like, this is what every other sine graph is derived from, which is a sine times bx minus c, and that a is usually equal to 1, b is equal to 1, and c is equal to 0, and it would produce this graph here. But moving on to the different portion of how it can affect a parent function is the amplitude. Now, the amplitude affects the height of a graph. For example, if it's just the height of the graph. So notice how it goes all the way up to 4 rather than 1 is because the amplitude has changed, but the period hasn't changed, and that it is about 6.28, which is right here, and that's 1 period. So 1 period is going up and down and going back over here. That's still 1 period. However, the only difference is that the height has changed. This also applies to the negative portion, in which the negative portion is also 4. And moving on to the next variation of a parent function, this is still what it looks like in case you forgot. The next variation is the period. Now, the period changes in that it reduces like kind of the frequency in a way. And so this is what changes is b here. And so popping up this port here, to find the period, you would need the parent period. In this case, sine and cosine is 2 pi over b, and b is 4. So 2 pi over b, you would have 2 pi over 4, and then you would have pi over 2. So then your period would be pi over 2, and that would be every time the graph repeats itself. Or in other words, it would be 1.57. Popping up the expanded view here is that the period is still the same, and that 1.57 is around here. That's 1.5. This is about 1.57, and so the period goes up and then down and goes to back 1.7. Now, the next variation of a parent function is the phase shift. And what a phase shift does is that it moves the starting point of the graph to a different location. What this changes is the c value here. And so to find the phase shift, you would solve for x, in which you would pretty much set the whole parentheses equal to 0. So in this case, you would set it x minus 4 is equal to 0, and you would find it for x equals 4. So then the starting point of the graph would start at 4. Popping up the expanded view here, you can see that the starting point is in fact at 4, and that it would continue how it would continue as in any normal graph, except just the starting point is different. Rather than starting at 0, like the parent function would, it starts at 4. Now, cosine and sine are very similar in that they both follow the curvy format. Rather, the only difference of cosine is that the starting point starts at 1 on the y-axis. Now, I'm not going to go into too many details as to on the differences, but they are very similar. So just briefly going over this is that the amplitude is the absolute value of a. That also applies to the sine graph. And so how you would change this is that the a can be equal to 4, and you can see that the amplitude is different here. Now, the amplitude doesn't mean you go from the starting point up 4. It means you go from the midline up 4. And so in this case, the midline was 0, and that you would go up 4 here. This also goes all the way down to 4 here. So you wouldn't be going 1 plus 4 is equal to 5. No, you would go from 0 plus 4 goes all the way up to 4 and goes all the way down to negative 4. And this also applies to the expanded view here. So you can see that this goes all the way up to 4 and goes down to 4, and that's the amplitude of cosine. This is also the variation of a parent function, in case you forgot. The next variation is a period, in which the period can change as the cosine would, and it is also similar to the sine graph. However, the only difference is that it starts at 1 rather than 0. And so the parent period would be over b, and the parent period still 2 pi over b, and b is 4, and that would be pi over 2, or 1.57. So the expanded view here, it's about 1.57 every time the period. And the period for this is that you know it's a period when it goes all the way down and then comes back up. So at the second climax is a period. This is 1.5, and this is 1.57. So you can see that indeed the period is correct for this cosine graph. And also the same variation for a sine graph also applies to the cosine graph for the phase shift. As usual, the phase shift is equal to 0, and then you set it to 0, solve for it, and you would get 4. So then the graph moves over to 4. And then you wouldn't start from 0 on the y-axis. This is the x-axis, this is the y-axis, but rather you would start up from the y-axis here at 1, and then you continue your graph. Now, moving on to the tangent graph. As stated before, the tangent graphs are different in that their period repeats every pi rather than 2 pi. So looking at this graph, you can see that I put the asymptote here, and the asymptote basically means that this red part here cannot touch the asymptote. Even though it looks like that it's getting really close, it'll just keep on going on forever and ever until it gets really close to it, but it'll never ever touch it. So every single x value in between these asymptotes exists on the y-axis, except this part here. And this part here is half pi. And same thing with the sine, you would have amplitude as a variation. So the amplitude here, to find it, you would find the quarter point, basically this point, which is pi, because this whole line here is equal to pi. And that the starting point is the midpoint of the graph, and then the quarter points is where the amplitude is. So to find this, you would basically find the midpoint of between the midpoint and the end point. So you find the midpoint here, and then your amplitude, whichever number is stated, is 4. So then you put that point there, and then you know that the midpoint right here is the starting point. And then you would find the quarter point here, and you would go down to 4, and it would go to 4. So that's how you would find the amplitude. And of course, you'd have the period. I already have the period here, 0.78. So the period can change in that the parent period over b, and I put the parent period because it's a more generalized formula rather than saying 2 pi or pi. This applies to different functions like the tangent graph. Like I stated before, the period is pi rather than 2 pi, and so b here is 4. So you would have pi over 4, which is 0.78. So that means it repeats every 0.78. And here you can see that this is exactly 1 pi in length here, and that it changes every time here. So the period is a bit shorter. And then next up, you also have the phase shift. This also applies to the tangent graph. And of course, solving for this, you would just have 4 popping up the expanded view. Instead of having it at 0, the midpoint is right here at 4, and then you'd continue graphing it as you would with any other graph. And so reciprocal trigonometric functions with examples and pictures. The principal values here is that sine x is equal to 1 over cosecant x, or in other words, sine is equal to opposite of hypotenuse. Cosine is equal to 1 over secant x. In other words, the adjacent over a hypotenuse, which is more widely used. Same thing applies to the sine of x. The tangent of x is equal to 1 over cotangent of x. And something not a lot of people speak about here is that the tangent is equal to sine over cosine, even though this doesn't apply to trigonometric functions that widely, it's still used in other areas of math. So tangent of x is also equal to the opposite and adjacent, and so this one, and these ones are the ones we'll be focusing mostly on this presentation. And then you also have the vice versa of this one. Cosecant of x is equal to 1 over sine x. In other words, the hypotenuse is over the opposite. Notice how the cosecant and sine values are switched. For example, in sine, it's opposite over hypotenuse, but when you find the inverse, it's hypotenuse over opposite. This also applies to the secant version. Notice how cosine is adjacent over hypotenuse, whereas over here is hypotenuse over adjacent. And then you would have this one here where you would have adjacent over hypotenuse rather than opposite over adjacent. And then also in the other aspect of tangent and principal values, you would have cosine over sine rather than sine over cosine, but that doesn't really matter. So to use principal values for this, sometimes you'd be given a triangle and it's got these values here, and these values aren't to scale obviously, because if you use Pythagorean theorem it doesn't equal 15, but for this example it does. So we're trying to find this angle here, hence ABC, and so the middle letter is usually the one that we'll be finding. So first off, you would have the cotangent. Cotangent is equal to the adjacent over hypotenuse, as stated before in the previous slide. So the adjacent, which is 12 over the hypotenuse over 15. So that would give us 12 over 15. Next example is evaluate, if possible, the given trigonometric function secant theta at the value of theta equals 2 pi over 3. So popping up the unit circle we first saw in the first few slides is that we would have to find 2 pi over 3. So looking at these radian measures here, we would see that 2 pi over 3 is here, and that the degree version of 2 pi over 3 is 120 degrees. But more importantly, we'd be looking at the coordinates of this point, which is -1/2 over root 3 over 2. Now -1/2 is the x coordinate here, so traveling backwards, make sure that it's negative if you're traveling backwards, since it is on a coordinate plane and isn't just a random circle. You'd be traveling backwards here and backwards, so you'd be -1/2 is right here. So yeah, that looks about like -1/2. And then since you're going upwards, it's still going to be positive, so you would have root 3 over 2. Now root 3 over 2 is 0.866 in decimal form. If you want to punch that in your calculator, you can. So 0.866 is close to 1, which is about right here. So these coordinates are correct. Now if you draw a triangle here, is what it's really trying to tell us here, is that if you draw a triangle, it would form this. But moving this triangle aside to have a better view and then expanding it, you can see this is the triangle we are formed when you have 2 pi over 3. So as said before, this side is root 866. I couldn't put the root sign into the slideshow, so I just put it in decimal form. So this is the height of the triangle. Then you also have the width of the triangle, -0.5. And then using the Pythagorean theorem to find the last side is 1. And then since we know that this is a 90-degree triangle, since we drew the line straight down, this is 90 degrees, and 120 degrees is here. So then we're trying to find this angle here, or rather this angle here. So that would be 180 minus 120 would give us 60 degrees. And then since the triangles always accumulate 180 degrees, 90 plus 60 is equal to 150. 180 minus 150 is equal to 30 degrees. So now that we have all our values here, we can find out the secant of this part here. Now you always want to find the angle that's connected to the base of the circle. This is what you would call, not really the base, but the center of the circle here. So since we took the triangle out of this spot right here, and that you would move it to the side, we would be finding this one since it's connected to the center of the circle. So getting rid of that unit circle and having a little bit more space on here, you basically, the secant is equal to hypotenuse and adjacent, if you forgot. So the hypotenuse is 1, and the adjacent angle adjacent to this one here is -0.5. So our answer would be -2. And then graphing inverse trigonometric functions. Inverse trigonometric functions is basically cosecant, cosecant, and some other ones like cotangent and like cosecant, sine, whatever, doesn't matter. But cosecant here, you would have this, and then this is what the function would look like for a parent graph. And basically, to find this, you would have to find the inverse of the y coordinate of the original function, as I call it. And so you do that, and then you would find the y coordinates of every other one. So here's an example. Y is equal to negative 6 cosecant times 1/2 plus pi over 3. So first you want to graph the original function. For example, the original of cosecant is sine. So the phase shift, remember, you would have to set everything inside the parentheses equal to 0. So then you would minus both sides by pi over 3. You would get x over 2 equals negative pi over 3. And that your starting point is negative 2 pi over 3. So next up, you would have to find the period, and that the parent period, is equal to the parent period over b. Now we are dealing with a sine graph, so then the period is 2 pi, and that b is 1/2, because 1/2 times x is equal to the same thing as x divided by 2. So then you would get 4 pi. So our period is 4 pi, getting rid of that. And then our amplitude is 6 because it's the number in front of sine, and that you would find the absolute value. If it's got a negative in there, it doesn't matter, because that's what absolute value means, is that the value is always positive. So then if you graph all that, then this is what your graph should look like. Notice how the starting point is negative 2 pi over 3, and that the period is 4 pi long. So you'd go, since this is a sine graph, it would start at 2 pi over 3, which is right here somewhere, right around whatever, and then it would go on to 4 pi, and then the amplitude is 6, so then it goes all the way up to from here to 6. And that there are asymptotes where the graph touches the midline for the parabolas. So once you put in the parabolas here, there are asymptotes every time it touches the midline. In this case, the midline is the x-axis here. So if there's an asymptote here and there's an asymptote here, just to help you guide your parabola drawing. So what you want to do from here, what you want to do from here is that you would have to find the y coordinate of this, and then you would find the inverse, which is basically the y coordinate is the power of -1, and then you'd plug and plug and plug and plug until you have a parabola and you could draw it. Now finally, moving on to the inverse of the cotangent and tangent. This is a mistake, this should be 3. But anyway, so we'll be focusing on these two lines here the majority of the time. So this is the line that's given here. And so you would put this down, and then basically their midpoints, or the starting points here, which is the midline or the midpoint of the entire period, is about a period apart. So it may vary on depending on what kind of period you have. For example, the period can change. It's not always pi or half a pi. So you'd have to find the period. In this case, the period was pi if you solve for the period here. And so they're pi apart. Notice how their asymptotes, or the amplitude, crosses right here. So it's pretty similar in that you just graph the original function here, and then you move it a period apart, and then just graph the inverse function. Now notice how the original function here goes from the bottom up, and it's always traveling in a positive direction. If you're going from left to right and then it's going up, then it means it's in a positive direction. But a negative direction means you're still going from left to right, but you're going downward. So just to make sure, you would always have to look at the left and then guide your pencil down and see if you're going down. If you are going down, then that's a negative function or an inverse function. But in this case, since this is positive and this is positive, then they're both the same function, or inverse functions. And that's pretty much the same thing. Now it may be a little tricky, but it's pretty much the same thing as the other ones, except you don't find the y coordinate and to graph, but rather they're just the midpoints are a period apart, and it's kind of like a reflection. And here are some 10 quiz level practice problems as one of the requirements.